So let's take a look at the 1993 AP Physics C free response question number 3, which is a neat little problem. And you see this a lot. They like to hang beams by threads. Okay. And by the way, those of you going on to study engineering, you'll take this wonderful class called Statics and Dynamics. And it's just this kind of stuff up the wazoo, okay? I don't know what a wazoo is, but whatever a wazoo is, you're going to get a lot of this, okay? And so here's what we've got. Let's zoom in a little bit. So first thing you should do when you look at this, you got to read the problem. You just got to take the time to read the problem. But one thing I do is I automatically start thinking free body diagram in my head. And when you get a beam that's held by a thread, they're probably going to cut the thread. So now you're going to have a problem where it's going to be rotating. So you have to think about torque as well as force. So anyway, that's kind of what I first think about when I look at this beam. It says a long uniform rod of mass M and length L is supported at the left by a horizontal axis into the page, boop, and perpendicular to the rod is shown. The right end is connected to the ceiling by a thin vertical thread so that the rod is horizontal. The moment of inertia of the rod about the axis at the end of the rod is ml squared over 3. See, that's nice. They give that to you. They don't expect you to memorize it or derive it. Express the answers to all parts of this question in terms of m, l, and g. Okay, yay, you don't have to use a calculator. All right, so A, determine the magnitude and direction of the force exerted on the rod by the axis. Okay, so here's my, so this is part A. So here's my rod, and here's a thread, and I'm just going to draw the free body diagram. So I've got this. Now here's my center of mass. So go ahead and draw the little center of mass symbol. And I've got mg pulling it down. Then you've got this axis. Now, in looking at this, you have to be really careful. It's pinned down right here. You could have a situation where the thread, like let's say they gave you a problem where the thread was at an angle. They could do that, right? Then you got to worry about horizontal force. But no, I've seen it. It's not, and it's. I've seen it, yeah. Oh yeah, yeah. It's not very nice. But these people are not very nice people.
They give you a lot of extra credit for it.
Yeah. Oh yeah. Oh yeah. Now. Yeah. So anyway, you're going to have some kind of force, but I can tell already that the force exerted here at the axis will have no horizontal component because these forces right here are vertical. And all this force is going to do is bring this into equilibrium. So I'm just going to draw it. There's my unknown force right there. So I'll just call this, I'll call this F sub T for the force by the thread. And here's mg. Or you can call it T for tension force if you want, because it is a tension force. And I'll just call this as my unknown force, F. And make sure I'm doing this. And let's see, they are using torque to do this, but so if you look at this just in terms of force, your intuition can lead you to the right answer. I mean, look, this is a uniform beam. You got the weight in the middle. Okay, so this is at the very end. This is at the very end. So this is going to support half the weight. Okay, so really I can just say right away, okay, F equals mg over 2. Right? Is that what you guys did?
No.
Absolutely. That's what I did. But I only got 1 point because I didn't show my words for it. So
Yeah, I know. Well, okay, but I mean, you got to show your work for it. So if you sum the forces in the y direction, that's going to be equal to F sub t plus F minus mg. Am I still on camera? Yeah. And it's in equilibrium, so all of this is going to be equal to 0. Here's the problem, though. This is an unknown force, and this is an unknown force. Really, in this equation, there's two unknowns. Now, you use your intuition, and you say, look, I know that these are going to be equal. Why? Because I've carried things before in my life. And I know if it's uniform, and you got one end, and I got the other end, it's going to be half the weight that we're each supporting. And you'd be right. Okay, but here in our world, our little physics world, we're not allowed to do that. So, what I'm going to do is say, I'm going to use torque instead. And now the beautiful thing about torque is that if an object is in equilibrium, it means there's no net torque. That means it doesn't matter where you measure the torque from. The torques have to add up to 0. Well, I don't know what this force is. I'm trying to find this force. So, pick your pivot point to be where the unknown that you don't care about is. Because then it's not in your equation. Does that make sense? Yeah, you just, by choosing your pivot point to be where one of the unknown forces is located, you've eliminated it from your torque equation. Isn't that sweet? Well, you could say that, but how are you justifying saying that?
Because the center of mass is in the middle. You have no mathematical.
Well, okay, but what you're doing there, and you're absolutely right, what you're doing there is you're intuitively doing what I'm about to do explicitly, and explicitly gets you points. All right, so if I sum the torque about this point right here, I'll put pivot point right there, then this torque, we'll say a clockwise torque is negative, a counterclockwise torque is positive. So this is going to be, if this is L, from here to here, this is L over 2, from here to here. So this is going to be R cross F, which is L over 2 times mg. And that's going to be my positive torque, minus this torque, which is just going to be L times F. And that has to be equal to 0. So divide both sides by L, and you get F equals mg over 2, which you knew anyway, right? But we just proved it. And it's going to be up. That's good enough. Well, probably not if you actually drew a picture of it, but you have to give them some indication that it's up, because it could be down. I mean, it's not going to be down. It's not down. It's up. Or it could be to the left, or up and to the left. So, yeah, tell them the direction.
Are you serious?
Yeah. That's the only
But to really prove that it's mg over... Now, hey, by the way, if I took this equation and now I plug it in here, you'll get that the tension force is mg over 2. So yeah, these two forces are equal to each other. But it's torque that allows you to prove that they're equal to each other. Okay. Now, the thread is burned by a match. So, okay. I don't know why you... Okay, for the time immediately after the thread breaks, determine each of the following. The angular acceleration of the rod about the axis, the translational acceleration of the center of mass of the rod, the force exerted on the end of the rod by the axis. Oh dear. Okay. Oh no. All right, so here's our situation. So here it's pinned at the very end. So now we do have an object that's rotating. And if I draw the free body diagram, we've got this. And at this very instant, here's mg. And then we've got some unknown force. I don't know. It's not going to, I don't know. I'll just put some force like this. Now, if this object is no longer in equilibrium. And so for part B, we want to know what is the angular acceleration about the axis. Well, this is my pivot point now. It really is a pivot point. And so part B is actually pretty easy if you know what equation to use. This thing has a net torque on it due to its weight. And that net torque will cause an angular acceleration. So the net torque equals I alpha. Oh, yay. Hey, your practice tests are here
How come
for
they always
tonight.
come the same day?
Sorry, guys.
She's a little touchy today, you know. I don't know.
I don't
Oh,
know.
you need
Yeah.
this.
Thank you.
Yeah, don't take that.
No, take the test back.
All right, and so here we have, so alpha is going to be equal to the net torque over I. The net torque, what is the net torque? The net torque is just, at this point, it's L over 2 times mg. Now, this is at the instant the thread has been cut, so it hasn't had time to move yet. So its angular velocity is still 0. At t equals 0, the angular velocity is 0, but it is angularly accelerating now. That's not 0 anymore. So this is just going to be, r cross f, which is L over 2 times mg over I, and so I, what did they give it as, m L squared over 3, I think was what they gave us. So the m's cancel as they tend to do, let's see here. One of the L's cancels, yeah. Okay. Oh, and that cancels the meter and the G. So we get 3 halves, right? G over L. Is that right? Yeah, there we go. Okay. So there's my angular acceleration. Now, and that's my answer for part B. Now let's do part C. Let's see if we can squeeze it in down here.
Wait, can you show part B for a second?
Yeah, there we go.
Thank you.
But I mean, look, here's my basic equation, and then
I got a point for writing that down.
yeah, write it down. And you know what? That's an important point. Okay. But so anyway, now we've got part C. It says the translational acceleration of the center of mass of the rod. Well, the translational or the tangential is another word for it. Remember that tangential acceleration is equal to r times alpha. That's the basic equation. The linear acceleration is equal to r times the angular acceleration. Remember those angular to linear equations, right? Where we have delta s, that is the arc length I go, is equal to r times delta theta, and our velocity, our speed actually, or whatever, is r times omega. And this is our tangential acceleration, is r times alpha. Remember, though, there is another acceleration when it has speed, and that's the centripetal acceleration. So acceleration is a little more complicated. But anyway, this is the equation we're going to use right here. And so we say, well, we know what our angular acceleration is from part B, but we also know that r is equal to L over 2, because that's where my center of mass is. And then alpha is just 3 over 2 times G over L. And so this, over L. Yeah, why the heck did I do that? Just to see if you were awake. All right. So the L's cancel, and we get 3/4 of G. So the angular acceleration of the center is 3/4 of 9.8 meters per second squared. But we can leave it in terms of g. So 3/4 of g, and that's my answer. Well, now for part D, it says the force exerted on the rod by the axis. So here's my this is for part D. So we want to know what is this force right here. Well, let me redraw the free body diagram real quick. I'll just draw it a little bit smaller, squeeze it in there. So we've got this force right here. We know we've got mg. Now there are no other horizontal forces. So look, your force is just going to be like that. But the center of mass is accelerating. So if I sum the forces in the y direction, that will be equal to ma in the y direction. And so we've got my unknown force. I've got minus mg. And this is going to be equal to ma. But a is 3/4 of g. So it's m times 3/4 of g. And so I'm going to but you know what what mistake did I almost make? What direction is this acceleration in? It's down. So I really should put a negative in there. I know they didn't in the solution guide, but it won't hurt to put it in there. So this is negative. So when I add mg to 3/4 mg, I get a force that is 1/4 mg, 1/4 the weight. So this is kind of an interesting result that, okay, when you were up here with part A, this force was half the weight. But as soon as you cut that string, you cut the string, you get this. Now the force that the axis exerts, at least at that instant that you cut the string, it's 1/4 the weight. And so there you go. All right. Now for part E, what is it asking for? The rod rotates about the axis and swings down from the horizontal position. Determine the angular velocity of the rod as a function of theta, the arbitrary angle through which the rod has swung. Okay, so here's off screen. Okay, let's do part E over here because there's a little room. So let's take a look at this thing at some arbitrary angle. So here's the rod, and here it's pinned down here. And we'll say that it's dropped some angle theta. Now, they want speed, angular speed, okay, angular velocity. Whenever they ask angular velocity, think energy, okay? Because energy, what's in energy? Kinetic energy. 1/2 mv squared or 1/2 I omega squared. It's there for you. So, and energy is almost always easier to deal with than kinematics. And by the way, kinematics really won't work in this problem, the kinematic equations, because the angular acceleration is not a constant. Right? The angular acceleration is maximum here, but the farther down you go, the less angular acceleration there is. So trying to use force or torque or kinematics is really going to be impossible. So you have to use energy, really. So here's my center of mass. Now, what I'm going to do is say there are I'm going to start with this. The work done by a non-conservative force equals a change in mechanical energy. Okay? But there are no non-conservative forces. So that means that this is equal to 0. This is E final minus E initial, which means I really can start with E final equals E initial. Now, what I'm going to do here is this. I'm going to say there's two kinds of energy going on here. There's rotational kinetic energy, and there is gravitational potential energy. Now, the nice thing about, we know where the center of mass of this is. So when the center of mass drops, you've dropped in gravitational potential energy. So let's make this is E at E initial, what we can do is say this. Let's make U sub G equals 0 right there. In other words, this is my reference. So at my reference right here, where theta is 0, where it's horizontal, it has 0 gravitational potential energy, and it's not moving yet. So how much energy does it have? It has 0. So we're going to set it equal to 0. Now, when it drops, I'm sorry. Yeah. Let me just do this then. Now I'm good. All right. All right. So now, E final. What is E final? Well, it's got two kinds of energy now. It's got gravitational potential energy, mgh. Now that's going to end up being negative, that h. That's why we can swing it to the other side and we're going to be okay. Plus 1/2 I omega squared. And that's what we're looking for right there. Now, let's do this. We can solve for omega now. Omega is going to be, let's see if I can do this in one swell swoop. All right. So we're going to have minus mgh over there. And then we're going to take all of that, and we're going to multiply it by 2, divide it by I, and take the square root. Okay? Now we can plug in what we know about I, and we can plug in what we know about h, and then we'll essentially be finished. Oh yeah, but it's going to go away because this h is negative.
The H is negative, Jason.
So this is going to be, let's just eliminate that negative. We know that h is down, so that's going to be that. So this is going to be mg. Now what is h? Well, in terms of theta, yeah, this is L over 2. The hypotenuse is L over 2. So this is going to be, h is going to be equal to L over 2 times sine theta. And there's our function of theta we were looking for. So this is going to be L over 2 sine theta. And then we've got the 2 over here. Oh, that's going to cancel the 1/2. That's kind of nice. And then we've got I, which is ml squared over 3. So now all we got to do is clean this up, and we'll have our answer. So omega is equal to, okay, we got an L canceling that. We've got an M canceling the M. We've got a 2 canceling the 2. And so what have we got? We've got square root of 3g sine theta. 3g sine theta over L.
Yes.
And that's our answer, isn't it? Okay. So, okay. So this one, hey, if you on this problem, if you had the basic concepts down, it was, I mean, it's a very doable problem if you have the basic concepts of torque down. Okay. Any last questions on this problem?
Like, I keep taking the wrong paper.
Oh, yeah.
Where'd it go? Oh, at A?
Yeah?
How you said it when you move the pivot? No, wait,
I put the pivot over here. Now, here's the key. If the object is in equilibrium, you can put the pivot point anywhere you want, because no matter where you measure torque from, it's got to be equal to 0. Because if there was a net torque, it would start to rotate. It wouldn't be in equilibrium. So when somebody says, hey, it's in equilibrium, it's static, you know, you can, hey, I can put the pivot point anywhere I want.
So when you did R cross F, how come it's the whole length?
Huh?
How come it's the whole length times the force?
Well, that's where, look, R, when you have torque, equals R cross F, right? Well, what is R? R is the vector from the pivot point that you chose to the application of the force. And so your R is all the way across. I'm sorry, I didn't draw this very well. L is all the way across. Does that make sense? Okay, that is all.